Hello all, I am Dr. Karthika from Department of Biomedical Engineering, SNS College of Technology, Coimbatore, and in this December lecture series we are discussing about biocontrol system topics, and now we are going to discuss about heart and systemic circulation combined and modeling of biological systems. Here, in heart and systemic circulation combined, first consider the heart and systemic circulation components of the model together and allowing the system to operate in a closed loop mode. Assume the following parameter values which have been chosen so that the model provides a first approximation to the human cardiovascular system under normal resting conditions. Here normal resting conditions are listed, and the interaction between two curves yields the steady state operating point, and which is labeled as N. This is established at cardiac output of 5L min minus 1 and PM of 0 mmHg, which are all the normal basic parameters used in heart and systemic circulation combined. See here, the heart and systemic circulation combined. The first one is QC and QR and PRA. QC is here heart rate. Heart including pulmonary circulation. Including pulmonary circulation means heart plus lungs. And we have systemic circulation over here, QC, QR and PRA, arterial pressure. Here, see the diagram. Here the cardiac output are venous return L min minus 1, L min power 1, L min minus 1. Here the cardiac output curve and venous return curve are shown here. See here, right arterial pressure PRA, which is denoted in mmHg. Same, see the next one, how it differs from cardiac output or venous return into cardiac output curve and venous return curve. Here the heart including pulmonary circulation and systemic circulation is represented in terms of QC and QR. Here the arterial pressure, right arterial pressure PRA plays a major role, and the curves which denotes the cardiac output as well as venous return. What is this N? In previous slide we have discussed the intersection between two curves yields the steady state operating point, which is labeled as N. See, the intersection of two curves is N. Okay, at the onset of exercise, the tensing of muscles involved plus an increase in venomotor tone, it produces a decrease in venous compliance, thereby raising PMs. Here, the sympathetic stimulation leads subsequently to an increase in heart rate, which elevates the slope of the cardiac output curve and increased vasomotor tone. Then, the local vasodilation of the muscular vascular beds, it produces a marked decrease in peripheral resistance. Here, new steady state cardiac output is now increased to minus J 10.5 L min minus 1, twice the regular value, while PM remains relatively unchanged at point E. See, the next model is used to predict the steady state values of cardiac output and PRA in heart failure following myocardial infarction. To represent the reduction in effectiveness of the heart as a pump, we assume that CS is increased and CD is decreased by 30%. In this way, if this were the only effect on the heart failure, heart output would decrease by 40% and the output is 3L min minus 1 point of F star. At the same time, PRA would rise by up 3 mmHg. See, here the regulation of ventilation, here the constant is K equal to VSTPD by VBTPS. It is equal to PB minus 47 by 863. Here in volumetric fractions, FiCO2 and FaCO2, it can be converted into their corresponding partial process PiCO2 and PaCO2 using Dalton's law. Here PiCO2 it is equal to FiCO2 of Pb minus 47 and PaCO2 which is equal to FaCO2 of Pb minus 47. Here PaCO2 which is equal to PiCO2 plus 863 VCO2 by Va. Here V is variable, and PaO2 which is equal to PiO2 minus 863 VO2. It is variable by Va. Actually, the terms are represented in terms of regulating ventilation. Actually, we use the concept to use the control system elements to map the physiological control system. So we have to equalize both the values here. Here the controller part of the system, it includes the neuronal circuits in the lower brain involved in the generation of the respiratory rhythm, as well as the neural drive to breathe and the respiratory muscles. The controller response of CO2 has been shown to be linear over the physiological range in the absence of vigilance, such as during sleep. The controller fails rapidly to zero, and the increase in CO2 response slope as well as the ventilatory controller output. See, the controller response of CO2 has been shown to be linear over the physiological range. In the absence of vigilance, such as during sleep, the controller output falls rapidly to zero. It leads to the increase in the CO2 response slope as well as the ventilatory controller output. That's all about output of cardiac output and ventilation output. Actually, which is called a combined feature of heart as well as ventilation. Thank you.